Okay, so in this video, I am going to be disagreeing with Norman J. Wildberger. But let me make something perfectly clear. I think that both constructivism and finitism, in fact, ultra-finitism, even if you will, are perfectly defensible stances to take in the mathematics of philosophy, and I think that there are good arguments for them. However, I do not think that the arguments that Wildberger makes ever are good, which is strange to me because there are good arguments out there, and for some reason he is not putting those forward. He is putting forward what I consider to be quite bad arguments, in fact. And so it is actually because of my sympathy towards these philosophical stances of mathematics that I'm making this video, because there is justice to be done for those stances, and I think that he's giving them a bad name by putting forward these poor arguments. And I should say, as a working mathematician, I, in practice, am not a finitist nor a constructivist. I suppose that yes. I think the one publication I have and the two preprints, all of them heavily depend on non-constructive mathematics and certainly infinite mathematics. But I think that mathematical pluralism is also a thing. We'll get into that in a second. Anyways, let's just dive in and see what he has to say here.
Okay, today we're going to talk about the notion of function, and I'm going to claim that this is like the emperor's new clothes, that the concept of a function really is nonsense from a logical point of view. So this is an unfortunate situation because the notion of a function plays such a huge role in so many areas of mathematics, not just analysis, but principally analysis. So let's start by looking at it from a historical perspective. In the 17th and 18th centuries, when calculus and analysis were sort of beginning to be developed, the notion of a function, say as elucidated by Euler, was that of a formula, okay, that you plug things in and you got things out. And the simplest formulas would have been polynomial or rational function formulas, which can be evaluated exactly. But also there were other kinds of functions, like the trigonometric functions, which had been used practically for a long time. But it was completely understood that these were not really exact things. They were only functions that could be approximately calculated. And that's the whole point of trigonometric tables, which go back.
So, sorry if this is boring. Yeah, we're going to go through the whole thing because I don't want anyone to be like, oh, I'm taking him out of context or something.
Thousands of years. Same with log tables. It was understood that these functions were only something that you could develop up to a certain precision level, and after that, they sort of devolve into obscurity. Okay, but in the 19th century, people wanted to shore up the subject, and this kind of ambiguity about what a function really was one of the major problems. And so people came up with an alternative. Dirichlet said, well, a function is simply a correspondence that takes an input and gives us an output. And later on, this became the set theoretic notion, where a function is a set of ordered pairs.
True. Okay, this is going to be a crucial point because he's going to say some stuff to try and argue with this. But yeah, definitely a function. A function is a set of ordered pairs, and in particular, a function from A to B is a subset of the collection of ordered pairs of A and B, with the property that for all A in A, there exists a unique B in B such that this there's a pair belonging to this subset. And really, when we write f at A equals B, this is really just a shorthand for saying that the pair AB belongs to the subset F. But okay, let's keep going.
Say you have a function from a set A to a set of B, then that function is described by a set of ordered pairs, where the first thing is in A, and the second thing is in B. And there's a kind of rule that says that every element in A appears exactly once as the first entry of all these ordered pairs.
Yeah.
So that's what a function is in the modern point of view. Okay, there's obviously...
So, side note, this is actually not entirely accurate. For example, well, okay, so for the purposes of this discussion that we're going to have with him, this is true. But just as a side note, you know, in modern day mathematics, we also have the world of category theory, which allows morphisms, which can be thought of as a generalization of functions, to be broader than this. Also, in algebraic geometry, functions are considered different. Because two functions may actually, it's possible to have two functions which produce the same output for every input, but which are not considered equal. And this is actually a really important idea in algebraic geometry. But okay, this is tangential to the conversation.
A couple of things problematic with that. Okay, first of all, what happens if you're considering set A, set B, which is an infinite set? Well, that means that
there's no problem. The definition still works.
Your function has to actually have an infinite amount of stuff in it. There has to be an infinite number of these ordered pairs.
This isn't a problem at all. Unless, and we'll get to this later because we're going to look at the comment section, unless you're claiming ZF or ZFC is inconsistent, but no one has a proof of that. And very few people believe it.
A further problem is that modern analysis really wanted a notion of continuity which went beyond that of the rational numbers, so-called completeness kind of property. And for that, these real numbers had to be invoked. Okay? And the real numbers end up being also infinitely prescribable. You need an infinite amount of data to prescribe a general real number. So what we're really talking about when we describe a modern function is an infinite number of ordered pairs. And if you look at any one of these ordered pairs, look in quotes, okay, what you see is, oh, there's an infinite, say, decimal in the first entry, then there's a comma, and then there's an infinite decimal in the second entry. And what about, the nature of these infinite decimals? Are they given by rules? All right. Is there a formula or an algorithm or some kind of variant of that which generates these?
Well, presumably he would know this, but the set of computable real numbers, which has a very precise technical definition, which I haven't discussed here, but of course it should line with your intuitions of what it means to be able to describe a real number by a formula. These have measure 0 in the real numbers. What that means is essentially 0% of all real numbers are actually computable. Even though, any real number, pretty much, most real numbers anyone has ever used, either theoretical or applied purposes, all happen to be examples of constructible real numbers. These are the ones we can actually get our hands on. Although, actually, I should say, since we are talking about constructivism, there are constructivist models of mathematics which still actually have real numbers, but in that case, all real numbers are constructible. So it's also interesting that I never hear him talking about these alternate foundations, because he appears to be a constructivist, but he's never bringing up these alternative, constructive models of the real numbers, which do exist and are perfectly sensible. But let's keep going.
These decimals, and if so, are those rules or algorithms visible, or are they sort of, invisible?
Well, like I just said, sometimes
it's a good question.
They are visible.
And if
0% of the time
these rules or algorithms are not there, then what kind of meaning are we ascribing to these infinite collections of information that constitute the elements of these ordered pairs? Now, in most treatments of analysis, this distinction is very much avoided because it's embarrassing. Okay, it's
No,
embarrassing.
no, just no. I mean, first off, it's not because it's embarrassing. Nobody is embarrassed by this. It doesn't matter, this distinction, for a lot of purposes. So it doesn't matter for a lot of purposes. B, like I just said, yeah, because we can only ever really get our hands on the constructible ones. Those are the ones that we tend to work with, and so that's fine. There's nothing wrong with that fact. Certainly, no one's embarrassed. And so, yeah, for the average working analyst, do they worry about the distinction between these? Probably rarely. But certainly plenty of people do worry about the distinction between these, in particular logicians and set theorists.
To have to worry about that. So let's take the cosine function.
And also there's constructivists.
For example, okay? Every pure mathematician on the planet, except for me and a few select others, believe that this is a legitimate function. The ancients didn't, Ptolemy didn't, the Arab mathematicians didn't, even the...
Well, what definition are we using for function now? Because a legitimate function, in the sense as a subset of ordered pairs, it is according to this definition.
16th, 17th century mathematicians didn't, okay? But yes, these days we do. So what is, say, cosine of root 2? Well, officially, cosine of root 2 is one of these entries in one of these ordered pairs. So cosine officially is a bunch of ordered pairs, and one of those ordered pairs, of the infinite number of them, is something that has root 2 as the first entry. So there's some infinite decimal corresponding to root 2. And there's then some second infinite decimal corresponding to cosine of root 2, which is something like 0.540, blah, 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 okay? But
Yep.
that's always what you get. You always get a few decimal digits, and then there's a blah, 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 or a and so on, or a and et cetera, okay? But the actual specification of those infinite things is never actually done, and it's impossible to actually...
So you can... That's just totally false. You can specify these things up to an arbitrary level of precision. So yeah, again, it depends on what you mean by specification. If you want a list where you can see every entry in a finite amount of time, well, that's not possible. But that's not even possible if it was just a very large finite number, right? And to be fair, an ultra-finitist would take the point that, there's some large number that we should take the cutoff, beyond that number, basically everything's meaningless. But
actually complete computation of the actual values that we're talking about. Okay, so this is a very serious problem that and covered.
So here's the thing: how could it possibly be a very serious problem? A very serious problem in what way? Does it introduce a contradiction into the foundations of mathematics? If so, that's a bold claim, and you need to provide proof of that. Is it a problem for real-world applications? Doesn't seem to be. The entire modern world in which we live seems to run just fine based on these ideas.
It's not just the cosine function, but pretty well all of the functions of modern analysis: the tangent, the exponential, the gamma function, the zeta function, modular forms from number theory, et cetera, okay? None of them really is a proper function according to the precise definition that analysts use.
In the specific case, right? If we're taking our definition of cos to be this series, this alternating series, then actually it's very easy to give an explicit description of the Cauchy sequence that we would want out of this, right? Because all of these are even exponents. And so we see that it's going to be the following is going to be given by the following. So we can actually take a Cauchy sequence representation of rational numbers. So we define Sk to be the kth partial sum. So this is the sum from n equals 0 to k of minus 1 to the k times 2 to the k over k factorial, right? So this is a sequence of rational numbers, and once you prove that this is a Cauchy sequence, that means it determines a real number. What is that real number? By definition, it's the equivalence class of that Cauchy sequence. So, for example, to explicitly describe the pair determining the value of cos at the root of 2, we take, it's simply, you take any Cauchy sequence you want that represents, you take the equivalence class of Cauchy sequences representing the square root of 2. If you want to be even more explicit than that, you could take, for example, A0 is 1, and AN is, what is it? I think AN minus 1 plus 2 over AN minus 1 over 2. By the way, if you're so obsessed with ancient Babylonian mathematics, this is known as the Babylonian method for approximating the square root of 2. And on that note, obviously you can make a triangle in the real world with two sides of length 1. What is the length of the hypotenuse then? Maybe you don't believe in the Pythagorean theorem, but again, we can't use we can't use real numbers in the real world, but it's still a useful approximation. Anywho, and so the point is, take this, for example, as this. What is the other pair? It's the equivalence class of this other Cauchy sequence. So boom, there you go. There's an element of the Cartesian product, which represents, cos squared. So yeah, according to your own, according to the definition, this is a perfectly valid thing to do. I can reproduce this more generally. I can give you the general result. It just relies on basic second-year mathematics results from Rudin.
Now, when you have a situation where mathematicians are divorcing themselves from their definitions, they have a definition over here, but they put it in a room and they close the door and say, we're never actually going to address this definition. We're never actually going to look at an object and say, oh, I wonder if this object actually fulfills the requirements of the definition. If you have that situation...
It does. I just demonstrated it does.
Folks, you're faking it. Okay? It's not proper mathematics. And we can get our AI machines at this relatively early stage of their development to kind of agree with us, right? We can kind of sort of imbue them with a healthy respect for the current status quo. But folks, this is not going to last long, right? These AIs are soon going to be starting to think at a much higher level than us, and they're not going to take our happy assumptions for granted. Okay? We're going to end up with a situation where all these
there's a lot to address there, but okay, let's somehow assume that these become superior logic machines, which so far they're definitely not that. But okay, there's interesting things happening at the intersection of lean and AI. Guess what? These things, these statements have already been formalized in proof assistance. Basic things about analysis have been formalized in proof assistance. So, what do you think the AIs are going to be using to check and prove these things? It's already proved by the computers.
Top AI machines that are doing mathematics are going to say, guys, I'm sorry, what you're doing is nonsense. We have to work in a computationally explicit environment where things actually make sense. Where
I guess we'll see. I guess time will tell.
Computations actually finish. Okay? And then we're going to have to...
Again, this is a perfectly defensible position, but the arguments he's making here are just bad.
Think about what functions are in a very different and probably much more limited way. So spaces of continuous functions, or spaces of C infinity functions, and topological vector spaces of functions, and then operators on those functions, and then operations on those operators. It's all really a mirage logically. And that's
I mean, if that's true, let's see the contradiction, right? If there's something actually wrong with this. So I already know from watching some video of his a number of years ago. I already know that he has a perspective. He denies formalism. He doesn't think that just because something is formally valid, that it's valid. But so I guess maybe that would be what he fires back with here. But again, let's see where the contradiction is in Foundations of Mathematics.
very sad story, and we're talking about perhaps what you might consider to be a bank that's too big to fail.
And also, I mean, don't get me wrong. He, at one point, used to publish a lot of perfectly fine mathematics papers. Actually, I was just looking. It does look like he has a publication from 2025. I haven't looked at it, but it just from the abstract, it seemed like a normal mathematics paper, just some combinatorics about the Catalan numbers. So fine. But like, let's, again, we shouldn't just take a herd mentality approach, right? It's a logical fallacy to just believe authority. But I'm imagining that there's a lot of people watching this who aren't mathematicians and who have not properly studied the analysis, as in Rudin, for example. And so understanding that, if you're watching this in that position, understanding that you don't have those skills to make this judgment for yourself, you kind of need to take a statistical approach. Who is more likely to be right? The vast majority of mathematicians, which includes like every Fields Medalist winner ever, or Norman J. Wildberger.
Okay, but the logical reality is that it just doesn't work. And you could verify
What do you mean it just doesn't work? It does, though.
this by just taking any, analyst or general pure mathematician and putting the name of a function in front of them, like cosine, and say, okay, show me exactly what cosine is. Whatever the definition of cosine is, please write it down on a page, and then let's examine whether what you've written down actually fulfills the requirements of the definition that you yourself have made. That's all you need to do.
I already did it.
And the whole thing just falls apart.
It doesn't. It doesn't.
Okay, so today, with the computer age and the AI machines, about to completely transform our subject, this illusion that we've been maintaining should be obvious. Okay, you ask a machine for cosine of 1. It'll give you 10 digits or 100 or a trillion, but it's not capable of giving you the entire thing, because the entire thing is not something that's actually in existence in the world in which we live in.
So this is an interesting point, right? Again, and here's a great philosophical stance to take. Sure, pi does not exist in the physical world that we live in. At least if it did, we couldn't ever tell, because we can only measure things to a finite level of precision anyways. Fine, but I mean, the thing is, all of basic mathematics does not exist. All of basic mathematics does not exist in our world. Like in the foundations of mathematics, like we define 0 to be the empty set, and we define 1 to be the set containing the empty set. This is notation used for the empty set sometimes. That's not in the real world. Like, find me the number 17 in the real world. You can find 17 of something. This doesn't exist in the real world. Natural numbers, whatever. So none of mathematics exists in the real world. Of course, there are people who take a stance of like hyperplatonism, where they do believe that all mathematical concepts are physically instantiated. So like, okay, you could believe that, but even if you don't believe that, I don't know. It's just, yeah, yeah. It's still useful though, right? I mean, there's no denying the usefulness that pi, no matter how you conceive of it, is in the real world, launching satellites and making sure they don't collide into each other. Like you just can't deny the practical utility of these things, even though they aren't physically instantiated in the real world.
That's just the way the world is. The gap between definition and reality, between wishful thinking and computational reality, is so large. It's undeniable now.
I mean, so again, it is true. It is true that there is a big gulf between those things in mathematics which are computable and those things which are not. But this does not mean that those uncomputable things are illegitimate mathematical concepts.
Okay, so it's a very interesting social question. Why does this illusion persist? Well, tradition, utility, professional inertia, sure. But there's also, a strong feeling of trying to buttress up all these theorems which we have ostensibly created. Okay? Most of these theorems, folks, I'm sorry, are not true theorems. They're just wish.
Okay, so disprove them. Where's the disproof of these theorems? Like, which theorems are you talking about? Like Rudin. I challenge, if you're watching this, open up Rudin and find a formal, rigorous disproof of this. Prove it in lean. Show us your disproof in lean, which would be very hard to do, seeing as these theorems have, a bunch of these basic analysis theorems have already been proven in lean.
Wishful dreamings. Okay, so that's all very sad. What's the alternative? How do we really make progress? So I think what we need to do is return to the understanding of the Pythagoreans 2,500 years ago. Namely that at the core of mathematics, there rests number. Natural numbers, ratios of numbers, like fractions, and proportions between numbers. Okay? These are a proper, solid computational basis for mathematics. And that's the spirit behind my work on rational trigonometry, universal hyperbolic geometry, algebraic calculus, recently box arithmetic. Okay? I think that it's exciting to think that we really need to return to classical Greek thinking, right, to create a more sensible, logical, correct, and computationally verifiable.
I mean, maybe there is value in that, right? Like I said, there's arguments to be made for constructivism and taking a computational based approach. And so best of luck to you in reformulating all of the most useful aspects of applied math and physics in this constructive formulation. I honestly hope that works out, and maybe we'll learn something new and interesting. But here's the other interesting thing. Why do you think that other people should not be doing mathematics that way? Like, why do you care, right? Like, if the math is logically valid, which it is until you provide a proof that ZF is inconsistent, you can't really contend with that. Why do you care then if mathematicians are off doing some kind of math that they enjoy? Why would you care? There's tons of logicians who are working in all sorts of freaky logical systems all day long. And they're all perfectly valid logics, right? There's many different axioms we could take for the foundations of mathematics. There's plenty of people doing constructive mathematics. And that's great. We don't need to commit to purely one foundation. It just doesn't make sense to be going on this tirade against other people not doing it, especially when, again, the proof is in the pudding. Look around you. Our modern world is built on calculus.
Mathematics. If mathematics is to remain honest, it must confront the illusion at the heart of analysis and find a more solid foundation in number. So the next time you see cosine of x written up in a textbook, remember, it's not really a function at all. It's an approximation procedure dressed up as a function. And perhaps in this age of computers, it's time to start telling the truth.
Okay, so Let's take a look at some of these comments, because there's some extra things I want to address here in these comments. Let's see. There's some things he was talking about. ZFC. Yeah, mathematics has always thrived on pluralism. Yeah, I mean, I wonder what he has to say about that. Pluralism, as in let's allow any kind of waffly argument. Okay, here's the thing. These other arguments aren't waffly. They're perfectly valid other logical systems. If it seems to make the job simpler. Pluralism also includes constructivism, by the way, which you're in favor for. Finitism is not a narrowing. I mean, yes, it is. And it's a perfectly valid narrowing. Yeah, what do you mean by make sense? If it doesn't make sense to you, tough. I mean, sucks to be you, I guess. I don't know. Let's see. Okay, yeah, so here. Do you think ZFC is consistent? So here's the big one he had something. I don't think so. Okay, again, let's see a proof. ZFC is actually almost completely irrelevant in the modern development of pure mathematics. This is an insane thing to say, because it is completely false. It is just completely false. I don't know what else to say. Like most of mathematics, modern mathematics depends on these axioms. It's just a convenient historical philosophical crutch that people can point to when challenged. What do you mean by this? Almost no modern analysis actually invokes these axiomatics. I mean, yeah, it does. I mean, do most modern papers cite any of the axioms? No. Why? That's the whole point of proving theorems, right? You don't want to have to go back to the reprove the same thing every single time. You think every single time you should start at the axioms and prove your way forward in every single paper? I don't think that you do that in your papers. So why would you have this? Why would this be what you're asking other people to do? Like, it doesn't make sense. In fact, horrible truth, most analysts, he's not an analyst, I would not call him an analyst, would struggle to even write down all the axioms of ZFC without recently having looked them up. Okay, they'd probably get 75% there, because again, we prove theorems, right? But the each of the axioms is being like implicitly invoked every time you use a theorem which follows from those axioms. With the axiom of choice the sole exception. Well, even there, most people just take it for granted and don't highlight when they're using it. That is trotted out routinely to justify another let's go to infinity and pretend it makes sense. Yeah, I mean, whatever. Just bad takes all around. So, anyways, that's gonna do it for this video. Argue with me in the comments, and QED.